Alright, so this is the lab 4 of Physics 2211, which is oscillations. So the table of contents, there's going to be intro, equations, experiment, computational model, results, and discussion or conclusion. So in the introduction, the purpose of this lab is to predict the motion of our system with the spring and mass, demonstrating fundamental principles. Motion is to analyze using tracker and a computational model used to predict the object's motion and plot predicted changes in energy. We'll try to prove energy conservation using an oscillating spring. We'll examine the motion of a spring mass system in which the mass swings in an arc while oscillating on the spring. The fundamentals happen to be Newton's second law, energy principle. And then the preview of the results, the change in total energy in the system will remain equal to 0, which satisfies the energy principle. So these are the essential concepts. The first one that we have is law of conservation of energy, which is the change in energy of the system is equal to the work of the surroundings plus Q. Then we have the spring potential energy formula. We have the kinetic energy formula, and we have the gravitational energy potential energy formula. We also have kinematic position and velocity equations. So our natural conditions, our system is a mass, spring, and Earth, and there are no surroundings in our case. I mean, there might be surroundings, but like we're not using any of them. We're saying that the spring force is equal to the force of gravity. So that means the spring force is equal to mg, and then this is just the conservation of energy law. So this is our tracker video. Okay, so you can kind of see the motion and you understand like what's the deal with it. So the values that we know, so we know the mass is 0.402, we know the position, the original position, that's from my calculations, and we know the original velocity is 0, 0, 0. G is obviously predetermined. We can calculate our spring kinetic using this equation by rearranging it, and we'll get 6.83. Then we can also count L0 by rearranging this formula. Mg equals negative k times magnitude of L minus L0. S is equal to magnitude of L minus L0, and L hat is equal to L over the magnitude of L. Sorry. So these are all the forces that we have. And the delta T is 9.2 seconds, which is calculated by the total time of movement of the oscillating spring in our video. So our code in action, once we put our code in, this is the graph that we get. So obviously there's delta K, delta U of spring, and delta E, which is 0, which is what it should be. XY graphs, these are our X position graphs and our Y position graphs. Sources of error, there could be various sources of error. For n, I may not have been precise enough while using tracker. My center of mass for every frame was not exactly at the center of the oscillating mass. There's also air resistance, and also our delta T might not be precise enough. So what does it mean? The energy principle is not satisfied because the total energy oscillates around 0. Kinetic energy should never be negative, but sometimes it is in our predicted model, which is weird. Given our X and Y graphs from slide 12, I predict that the period of oscillation from X position data is 1.6 seconds, and the period of oscillation from Y position data is 1.5 seconds. The difference exists due to calculating a spring constant that only accounts for using oscillation periods, not of a single axis. So in our conclusion, other forces were not necessarily taken into account. This could be a reason for differences in position data between experimental data and the glow script, the computational model. Thank you.